So welcome back, everyone. So thanks for coming. I know it's so for some of you it's snowing outside. It's been a long week for a lot of people. So thanks for coming back. So this is the point in our semester we're about 3/4, 2/3 of the way through. It's time to really recenter yourself on what you need to do well to finish up the semester. This lecture will be about centering, so that's great. So it's a technique that we'll see that's going to turn the SVD into solving this original dimensionality reduction problem the way we said at the beginning of this section. We'll also use it for another technique called MultiDimensional Scaling. And so some of you have asked about things like how can you do this unsupervised learning where you don't have labels, you don't know what the answer is. We'll hopefully kind of see why the SVD and principal component analysis and these ideas can be useful, even if you don't totally trust this unsupervised sort of setting. We'll see this MDS technique is kind of another thing which uses all the same kind of ideas and technology, but solves a different sort of problem. And this is just one instance of these. There are a few more within the textbook that we aren't going to cover, and many more in the data mining sort of literature out there. So let's look at the website. And before we look at the schedule, so there's a new video out there that was posted by Hassan. So the number of people had asked about kind of getting stuff working inside of Python, so inside of Collab. And there's a few steps which I think were a little bit tricky for someone, and we never really explained. So I wish I had Hassan do this a bit earlier in the semester. But so here now, he's got a tutorial posted right on the main page. I linked to it off of Canvas. Has stuff about if you're working with Collab, you need to be able to load files. There are a few different ways to do this. He goes through, you need to be able to process them and read them, and then some basic stuff with plotting. So just a review of stuff kind of all in one place, really the basics of what you need to know. So thank you very much, Hassan, for this video. So if you've been struggling a little bit with these aspects, hopefully this kind of really gives you some stuff to clear up. There's also the Python notebook attached that he actually works through is attached there, so you can actually see that other than just in the video. So again, if you have questions about this stuff, myself and the T's are always happy to help as well. So where are we in the semester? We're getting close to the end. As I scroll down, you can see the end of the schedule. So we're going to finish up the section on dimensionality reduction. And this lecture kind of is really going to hopefully tie everything together about we learned about this SVD and this unsupervised learning, and kind of how it's connected to eigenvalues and how you compute it, but how do we actually do the dimensional reduction? And there are many formulations to what dimensional reduction means. We talked about one, we'll solve that one, but we'll also talk about another one called multidimensional scaling. And we'll see how to do these in Python as well. And then after this, we're going to move on to the last two sections in class, probably kind of two of the most famous aspects of data analysis. So clustering and classification. And so those are going to be the last two sections, and kind of really setting you up for core things within data mining and machine learning. So you'll be able to kind of basically do kind of basic things in those tasks after this course. Well, not the full depth of what I think you really need to learn, and we have more classes for that. Okay, other than that, homework 4 has been posted. After today's lecture, you will have everything you need to know. A couple of questions maybe didn't they look like they made sense, but they didn't because you didn't have this lecture on centering in PCA, and hopefully that will tie some of those remain things together. It has a programming component, which is probably the one I've given you the least guidance on. It combines together linear regression and gradient descent together, where you have to read a file. We've pre-processed the file as much as we can, but you'll read it, and you're going to solve linear regression using gradient descent, like we talked about, okay? So something you can do in Python and Collab, and the tutorial Hassan has put together will give you the setup for that, but you're going to actually have to set up this formulation, which we talked about in kind of the lecture, the last gradient descent lecture. Okay, so this is kind of, it's for some students, it's just like kind of stacking together stuff you've known. For other things, it's kind of a lot. And this is kind of the one of the peaks of what you'll learn in this class, because this is a lot of how machine learning and data mining works. You take data, you build a cost function, and you optimize it with gradient descent. And so you're going to actually go in and do that in this homework. Okay, so this is going to be a cool thing that you will have done after completing this homework. But don't wait until the last minute again, because this one will take a little bit of time to get stuff working inside Python. So yeah, so okay. And then quiz 5 is going to come up. That's going to be in 1 week. Remember, we moved everything, a lot of stuff back 1 week because we took this extra day off. So last week. Probably no one would have focused on that day anyway, so that was probably a good move. So this quiz 5, it will cover just stuff in dimensionality reduction. Okay, so this will be the last lecture covered in quiz 5, and that'll be in 1 week. It'll be standard like the other quizzes. You'll get half an hour. You'll get one sheet of one side of the paper you can turn in for 5 points of credit as well. So, okay, any questions about the schedule so far? Yeah, everything's good. So if any concerns, I know we're kind of towards the, getting pretty far in the semester, but if like stuff has been, people have been having trouble. A lot of people are doing great in this class, and I'm really happy about that. I know other people have been struggling with, I don't know, some of it's the material, some of it's just everything else going on this semester, and I understand that. But if anything we can do, please let us know, and we can try and help with that. So okay, let's get to the lecture. Okay, so we are going to talk back about this dimensionality reduction. So problem. Okay, and we're given now input a set A, and let's think of this as a subset of RD, but so it's going to be A1, A2 up to AN. Each of these is going to be an element of RD, right? Each one of these. And we can define a distance between AI and AJ, and we're going to use the Euclidean distance, right? Which is just this so the 2 norm in between the vectors. Okay, and so this should be well defined, and we're going to want to find, the goal is, this is the input. The goal, remember, is going to be a low dimensional representation. Okay, and there's a couple different ways of thinking about this, and I'll kind of be a little fast and loose with the notation. I think I've been consistent with it, but there are a couple ways of thinking about it. One is that there's going to be a point set B, okay, which is going to be a subset of RK, okay, so which is going to be B1, B2 up to Bn, where each AI kind of corresponds with BI, right? There's this kind of correspondence between these. And I want to preserve the structure in A, but in a lower dimensional representation B. The other way of thinking about it is B represents this k-dimensional, so subspace of RD, and then I think we called this V sub B. This is V1, V2 up to VK, and I could define this by these unit vectors, these orthogonal unit vectors V1 through VK. And then the goal was more explicit here, that I want to minimize all the choices of B or of V sub B, the projection onto B of A minus A, right? So I want to minimize the error if I project A onto this low dimensional subspace, and this is maybe shorthand for what I really want, I equals 1 up to n of the projection onto B of AI minus AI. And we'll write squared here. Might as well write squared. It's this same minimum. Okay, so I want to minimize the sum of the squared distances of projecting. Okay, and so I'm going to think of having, let me see if I can think of we're in RD, and I've got a bunch of these points. These are A1, A2, A3 up to AN. And I want to find a subspace here. Right, so we'll call this subspace B. This will be k dimensions. And maybe I can define this by two basis directions, V1 and V2. And for each of these points A, I'm going to project them down onto this subspace, or down or up, you know, it doesn't matter what direction, but the closest point, right? So that point there is pi of B of AN. That's what this point there is referring to. So I'm projecting A of n, or each of these points in d-dimensional space, onto this lower dimensional subspace B. Okay, and I want to kind of minimize the sum of these squared, so distances. These green distances are now the residuals. So this would be Ri. This is a residual, kind of like we had with regression, but now it's projecting orthogonally onto the subspace, not in some magical y direction we had available. Okay, is this reduction only possible for numerical dimensions? I'm thinking you're asking for if the number of dimensions k is going to be a positive integer. So is that what you're asking? There could be other interpretations of what you're asking. Turns out there are lots of variants of this. Okay, so I mean for data that isn't recorded in numbers, the color of a car. Oh, okay. So yeah, so you could be doing something else where you have a data set. Okay, so yeah, so let me just mention about this in context. So alternative so problem. Okay, so there's this kind of what the question is asking is there's this alternative problem where you have data points, say x1, or you have some customers or something or people, and you've collected these are x1 through xn, but for each of them I've got these features. So this is f1, f2, F3, F4 up to F, let's say N. And so these features for each of them might be a number, 7.1, you know, this 8.3 up to 9.4. Like we had this example with the amount of jiggle of a mouse and scrolling and time. We had this example, but it could also be something like some sort of categorical variable. So it could be a feature 2 here could have to do with a color. So this could be blue, this could be green, this could be the color of the car that they own, right? You know, it could be black. Or what's typical done is that you would actually just, if you have a categorical variable, this is kind of hard to deal with. So what you would instead do is you would split this up into kind of 3 variables, F21, F22 up to F2K. And this one might come with blue. This one might be green. And this one would be black. And you'd have everyone's would be just 1, 0, 0. So you have, so you turn this into a binary variable. So you can only have a 1 in one of the entries, but now everything is going to be 0, 1. If you do something like this, it will work fine within regression and classification, or work okay. There's some things to maybe be worried about here, okay? But this will generally work okay there, but that's only because I have a particular value that I'm trying to predict against. That's not the case. I can't mix these. So let's say I can't mix. So numerical and so categorical in so unsupervised. Okay, it's in this unsupervised setting where I don't have a label. I'm so trying to predict here. There might be kind of some ways to do it with some labels or some stuff. If you look at kind of distance metric learning, which is later on in this chapter in this book, you can have other information which allows you to kind of learn how to do dimensional reduction, but you effectively need a different sort of labels to still, in order to still do that. I don't know how to balance the difference between 7.1 and 8.3. How big of a difference is that compared to kind of the blue versus green? So I don't know how to compare how much to weigh each of those quantities without some extra information. So if I don't know how to weigh those two things, then I'm just kind of guessing as I go, and you're kind of doing real black magic here, and just changing the units of stuff will completely change your answers. And so I like, people do stuff like this, and you'll see demos and stuff online where they're doing these sort of things. And I think it's kind of like they're just kind of going through it procedurally, but not really thinking about underlying the stuff that's going on here. If you treat these as if the distance between 0 and 1 is a distance of 1, and that's basically the difference between 7.1 and 8.1, then, and if you think that is the right way to balance it, then there's some stuff you can do. You're going to lose this green section here. It has some sparsity components to it, which means you can represent it more efficiently than writing down all these zeros. There's some techniques that preserve these, some that don't. Yeah, this comes into a play in like really big data. If you look at the very last section of the book, there's stuff on matrix sketching, which will be covered in the data mining class, and there are ways to deal with some of these things and preserve this structure. Do they really make a difference to do it that way? I think sometimes, but you're kind of getting into some more rare cases where that structure really preserving that structure actually really matters. Okay, so dimensional reduction is trying to reduce useless data fields while making sure the model is accurate. Yeah, so it's not, so dimensional reduction is generally not reducing entire fields, it's combining them together. Okay, if I go back here, I'm discovering these subspaces here, like this blue subspace. Well, look, that blue subspace I've highlighted is none of those original black subspaces, right? There were these original black axis directions. And that blue one I've highlighted, that first, maybe that first singular vector, whatever it is not any of those in particular. It's a linear combination of all of them, right? So it's kind of, it's in these techniques we're talking about in this class based on the SVD are going to find subspaces which are linear combinations of all of the subspaces. So it's kind of saying, I'm going to combine all of them together into a super one dimension. So a super dimension that factors everything in together into a single direction. I'm trying to make, think of like if you have data, okay, so here's another way of thinking about what's going on here. If I have high dimensional data, okay, A1, A2, up to AN, and these are all in RD, okay, then how do I sort these? So how would I sort these? From like, I want to give a one-dimensional ordering of them in some way, right? In one dimensions, you know how to sort, right? You're given single numerical values or just anything that has a comparison function. You can write down a sorting algorithm. If you've taken, I think it's in 2420, in any basic algorithms and data structure class, you learn how to sort, okay? But with high dimensional data, I don't know how to sort them. Depending on which direction I look at them, the ordering of them changes, okay? Okay, the one way to think about it is the first, so dimension I will find, V1 provides the kind of the best one-dimensional so ordering. Okay, so what I'm doing is I'm projecting down onto one dimension that's combining all of these attributes, and it's somehow trying to preserve an ordering that does not move things too much out of the way, right? So then I can get these values, V1 dot A1, V1 dot A2, up to V1 dot AN, right? This is going to give me n values, and then I can sort these n values, right? So if I was in this high dimensional space, right, draw this picture again, right? And I'm going to find this one-dimensional space, V1, and then all of my points are going to be projected onto here, and their values, their distance from the origin are these exact, the distances from the origin are going to be these values. That's the value of, so V1 would be that distance from the origin here of, say, A1. Okay, and so I get a one-dimensional ordering of them now. But maybe I want two dimensions because I want to see how they interplay a bit better. So then I add another orthogonal direction onto it and so forth. Okay, and this is the one-dimensional ordering that preserves the distances as good as possible. I've lost this least amount of noise information. So, okay, so we have not quite solved this problem yet. We've talked about something similar. We've talked about how do I find, let's go back and make sure I highlight this. We want to minimize, find the subspace which minimizes the sum of these squared errors, the sum of those green terms, this squared. I want to minimize that. And we didn't quite do that yet because the subspace we found in particular has to go through the origin, right? Which was 0, 0, 0. Okay, but I want to draw a picture now that's going to kind of make you hopefully realize why this is not so important. Okay. Okay, let's think I've got some, just in 2 dimensions here, I'm going to have some data points which are going to look something like this. Okay, so if this is my data, and you can think there's even more data points here. Okay, the first singular vector I'm going to find is going to do something like this, V1, and then the orthogonal component would be, say, V2. But this subspace is not really capturing what's going on with this data. What I'd rather do is to find a subspace that looks like this. Okay, I'd rather find a subspace that says, look, that mode of variation that I really care about is along here, right? This is the first kind of dimension that's going on, and everything else, you know, is kind of, there's some air projecting onto here, but most of the variation is coming along here, this green curve. And the right, these are the right singular, so vectors, these are not so good. Okay, so these don't do such a good job in this case, right? In this simple 2-dimensional case here. It turns out if you're trying to find a 10-dimensional subspace and you use the singular vectors, they're probably going to do fine. But when you go down to 1 or 2 dimensions, those figuring that first one out the right way is kind of is pretty important, and you don't want to necessarily use the right singular vectors. You want to find these green subspaces instead, and then maybe you have a second one here, right? But these are called the principal some components. Okay, when you do principal component analysis, PCA, principal component analysis, PCA, you're finding these green ones instead of these blue ones, which is giving you a much better approximation when the data does not necessarily go through this origin point here. Okay, you don't necessarily want it to go through this origin, which is what the SVD and the right singular vectors directly gives you. Okay, so that's the first thing we're going to talk about today, is how to fix this problem, and this is actually what we want. So it turns out that there's a pretty kind of simple solution to it. There's this point here called the center. We're going to do a trick called centering, where we're going to shift all the points so the center of the data set is at the origin, and then we're going to run the SVD. Okay, so that's all we're going to do. We're going to define the center. We'll call this I'll call this A bar. Okay, where A J bar, or let me just write it this way. A bar is going to be A1 bar, A2 bar, up to a D bar, and a J bar is going to be the sum over I equals 1 to n of AI J. This is divided by n. Okay, so this is going to be the average of the coordinates, right? So I take the jth coordinate of all the data points and I take its average. Okay, so the jth coordinate, the first coordinate of all these data points, is projecting down onto this axis, right? right? And then I take the average of all of these, right? This would be a 1 bar, right? And so this is the first coordinate. I do it with the second coordinate by projecting onto what's drawn as the second axis, typically the y-axis here, right? I do that with each coordinate. I get a center, okay? And then, centering of matrix A, okay, there are two ways of doing this. So two ways. The first way, so compute the center A bar equals or a d bar, where a j bar equals 1 over n aij, just the average of the coordinates, and then you create we'll call this a tilde ij. So each element is basically going to be of the matrix is going to be aij minus aj bar. So I just subtract off the center coordinate, right? This is kind of the first step we did in the kind of the explicit form of regression in 2 dimensions, where we realized the best solution for regression actually went through the center of the data set again. That's going to be the same kind of thing that's going on here, where we're going to find that the best solution that is not restricted to the origin is going to go through the average of all the data points. And so we move that average to the origin, and then we can revert back to our original solution here. Okay, there's a second way of doing this, which we'll see is convenient, and this will be built into this multidimensional scaling MDS idea that we're going to talk about kind of after we finish PCA, is with a centering matrix. Okay, so this is a matrix that does the centering for us, and it's linear algebraically more friendly. So C, this is for an n by n data set. So Cn is going to be the identity matrix, an n by n identity matrix, minus, I'll write out the common notation, then I'll explain it a bit. 1 transpose. Okay, so this is going to be the matrix with 1s on the diagonals, the identity matrix, and 0 elsewhere. That's n by n. Okay, and then I'm going to subtract off this 1 over n factor, and this is going to be an all 1s matrix vector, and then 1 transpose is going to be the all 1s row vector. And so this part here is going to be actually a matrix where every entry is 1 over n. So every entry there is 1 over n after I put that factor in front. Okay, so I compute this, basically the identity minus 1 over n everywhere. So this is going to look like most entries are, this is 1 minus 1 over n, 1 minus 1 over n on this diagonal. Okay, and then everywhere else is just 1 over n. That's everything that's off the diagonal, or is minus 1 over n. Yeah, so that's called the centering matrix. And then I can compute aij tilde as just the centering matrix times A. Okay, so this is, if you multiply A through, multiplying by the identity, right? If I look at what this is doing, that's A, because that's multiplying by the identity, minus 1 over n times this 1 transpose A, right? And so that matrix is computing. It turns out it computes in every column the average. It's the average in every column, and so I'm just subtracting that off in an element-wise way when I multiply through by this extra term. Okay, so that's what the centering matrix is doing. So there are two ways of doing this. I can compute it with the centering matrix, or I can compute it by computing the center in this way, and then I'm subtracting off this center here. Okay, so all this is doing is it's shifting the data set, right? So if I go back here, I basically am computing a new axis. I'll draw this in pink, right? Where the new axis now has an origin that lines up with the center. And if I run SVD, I'm going to get exactly the principal components I was hoping to get. Okay, so that means that principal component analysis, okay, is going to take as input a subset or an element of Rn times D, and a parameter k, let's say less than D, less than N. Let's say that. And then I'm going to output a B, which is represented by VB that minimizes, which is V1 up to VK, right? That is minimizing the sum equals I over 1 to N of the projection onto B of AI minus AI squared. Okay, so it's doing that, but with no restriction. It has to go through the origin. And how this works is that step 1, it creates a tilde, which is going to be CNA. This is through, so centering. Step 2, I'm going to get out USV transpose by the SVD of a tilde, right? So now that I've centered the matrix, I have still an N by D matrix. I still can run the SVD. I get out SV transpose, and 3 VB is going to be kind of this, these singular, right singular vectors still. So V1, V2 up to VK, right? So it's basically, I'm still getting out of the SVD as I've done this before. Okay, and if I want to actually get a subspace B, so say I want to get B1 up to Bn, well, what I can do is I can just do that B is going to be equal to V times A, or V sub K transpose, or yeah, so transpose, V sub K transpose times A. This is going to get me the points realized in B-dimensional space here. Okay, so I just multiply them, and then these are going to be elements. These are going to be a subset of RK. These are going to be k-dimensional points. If I want them to be so the d-dimensional points, I need to then add back. So if I want so k-dimensional points. Okay, let's call these B equals B1 up to Bn, right, where these are going to be in RK. Then I'm going to get B is going to be equal to VK transpose times A, which is going to be where each BI is going to be VK transpose times AI. right, this row of A, the original row of A. I'm going to transform it. What this looks like is I'm going to have these rows V1. This is our matrix VK transpose, which is going to be K dimensions here and D dimensions here. I'm going to have a matrix or a AI. Okay, and when I multiply this by VK, oh no, it's going to be a transpose. So it's going to be the row matrices. Okay, so let me write this like this. So this will be VK, and each of these is going to be VJ. So this is, sorry, VK transpose. And when I multiply AI by this, AI is going to be AI should be a column vector here. Okay, so this column vector here, then I'm going to take a dot product. So I should see this as doing a dot product. I'm going to get out this this k-dimensional vector, where this will be Bij, right? Each Bij is going to be the dot product between Vj and AI, right? I'm going to stack these up. This is going to give me all of the coordinates here. Okay. If I want so this is for the k-dimensional points. If I want d-dimensional points in a k-dimensional, so subspace, okay, then I need to do an extra step. Then what I want to do is get like this rank K approximation of the matrix. So remember, I'm going to do centering to SVD, okay, and so this is going to get me this. Now I'm going to want to use this centering vector in RD. I'm going to get USV transpose. So what I'm going to do for each point now is I'm going to represent a tilde sub k, which is going to be U sub k, S sub k, V transpose sub k, where I've just taken the first k components of each of these. This gives me the best rank K subspace. And this will be an element in RD, but in a k-dimensional subspace. And then I'm going to uncenter it. So I'm going to do a k without the tilde, let's say, and the ith j coordinate is going to be a k tilde. What is that? Tilde here, ij. So taking that, now I'm going to add back in a j bar. So I'm going to uncenter it now. I need to push it back up to that subspace again. So I need to undo the step of the centering. I did this centering matrix here, and now I need to have to undo it again. So this gives me the best k-dimensional subspace, and this gives me back the points on this green subspace that's projected onto there. So I need to I need to find the center, remove the center, do the SVD, find, project onto that low dimensional subspace, then uncenter it again. Okay, so that's what, if I want to get the d-dimensional, these d-dimensional points here, then I need to kind of do the SVD like I did before to get the points in RD. Oh, that's right. This should be an element of n cross d, right? So it's still in, yeah. And I'm still in an n d-dimensional points, but they're forced to go through this origin, then I push the center back into them. Okay. Okay, so that's principal component analysis. It's basically the SVD, but I have this extra centering step that I need to add in there in order to solve this optimally. And I'll mention the literature. If you read about this online, they will often confuse these terms, and this sometimes leads to problems. People want to find a low-dimensional representation. They just do the SVD. They forget to do the centering step, and this can sometimes make a huge amount of difference in what the results are because of this confusion. So in the textbook and this class, we're very clear the SVD is this numerical operation which finds a good subspace but forces it to go through the origin, right? So you know, just be clear, SVD best subspace through the origin, and PCA is the best subspace, not necessarily with the origin. It might include the origin, right? That could happen, but if the center of the data is already at the origin, like previously, all the examples I picked for the SVD, I think I discussed it until this lecture as going through the origin, but that's not necessarily the case. And so this kind of fixes this. So I want to clear one more thing up. So sometimes it's useful to talk about the subspace. So as saying V1 is the represents the highest variance, so subspace, and this is kind of used very similarly to what is going on with the probability notion of variance, right? If you remember, if I have a variance of a random variable, right? If I have a random variable x, then this is equal to the expected value of x minus the expected value of x quantity squared, okay? If you remember what the expected value is, right? So let's say that the expected value is something like taking an average, right? So let's say the sample variance. So sometimes we'll use the term variance and clean the homework, and maybe it's a little bit informal, but the sample variance of, we'll call this sample variance of x to be clear. Remember that this is, or the sample, so in order to do this, let's first talk about the sample expected value. Of x is basically going to be 1 over the size of x. So elements, let's call this, of the value of x, maybe times the probability of x. But that is often, these are really the same thing. So if the probability of x equals 1 over n, then this is equal to, or is equal to the size of x, then right, is just this value here. Okay, so if I plug this into a notion of the sample variance here, okay, I'm going to have the expectation over some x of x minus expectation over x of x squared. Okay, so if I want to think of the principal component analysis this way, that's good because I've centered it out, which is kind of removing this internal expected value here. So centering makes this 0, right? So what I want to think about for x, let's let x equal some v over ai for all of these for a1, v, a2, and I want to consider this for all the possible values v, and I want to say that the one I found by principal component analysis is going to, v1 I found from principal component analysis is going to maximize the variance. Okay, so variance needs to subtract out the expected value. So you could think of this as 1 over n times the sum I equals 1 to n. And this is going to be over the AIs now. And this is going to be v comma AI minus the expected value again, but the expected value was 1 over n I equals 1 to n v AI. Let's make this L because it's not the same index here. Okay, and so it's this quantity here. Okay, but by centering it makes this 0. So I've taken the average along every coordinate, and this is a dot product. So this term is going to be exactly 0 if I have centered. Okay, if I've not centered, then I'm kind of taking the difference from the mean, which turns out, so I want to maximize the kind of the squared error, the sum of squared errors, which is what SVD does, but I need to subtract off the mean in order to make this so it looks like the variance. So after I've centered, then this is 1 over n I equals 1 n of just quantity v ai squared, because that other term I had subtracted off is now 0. Okay, and this is exactly the quantity that the SVD and the power method maximizes by finding the first right singular vector as v. Okay, so that's why in some way the centering is like removing the average. So then what I'm finding is the squared difference from the average, which is the variance, and I'm finding the maximum variance direction. Okay. Okay, good. So this is what I want to say about principal component analysis. They're kind of like talked about a lot of different aspects, tied up some things in the rest of the time, unless there are some questions here. I'd like to kind of tell you a little bit about this other variant of stuff called multidimensional scaling. Okay. Multidimensional scaling, often called MDS. Okay, and so this is another dimensionality reduction formulation, but the input is going to be different now. Okay, my input is going to be one of, let's call this input A or input B. Okay, input A is going to be a set of n objects and so distance d. So I can compute a distance between things, or input B is going to be a D, a matrix D, which is going to be an R n by n. And so each Dij basically implicitly measures the distance between object xi and xj. Okay, so sometimes I'm given an n by n intrix matrix. Sometimes I'm just giving n objects and some notion of distance between them. Okay, so think of this as like if I have n cities in the US and there's and I can look at what's the cost of flying between those cities on an airport. That gives me a notion of distance. The higher it costs, the further they are away from each other. And because there's lots of flights between, say, New York and Los Angeles, even though they're far apart from each other, the price might not be as high as, say, flying from Los Angeles to, say, Philadelphia or Pittsburgh, which might be closer, but there aren't as many flights, so the competition is good. But so there are other notions like the distance I have to travel by a road measured in time, right? So if I can go on the highway, that's not too far, but if I have to go on back roads or kind of one of these dirt roads in Utah, then these are going to be further away from each other, right? So I want to take this data and I want to find the goal now is an embedding of n objects into, say, Rk, so in some k-dimensional subspace, k-dimensional Euclidean space. So the distance, let's call these, what should I call the embedding? Let's say as Q1 up to Qn, so that Qi minus Qj is going to be approximately equal to Dij equals D of Xi, Xj. Okay, so I want to find a low-dimensional embedding, often a two-dimensional embedding, so I can visualize it. This is a very common thing in visualization where you want to visualize data where you only get distances. Find a two-dimensional or low-dimensional embedding so that the objects I represent in that space are going to be approximately have the same distances as the ones I've been given. Okay, so this is a different formulation of the problem. Now I know I trust the distances, but I don't have a high dimensional representation. Okay, and I want to try and find this some low dimensional representation. So okay, so this seems similar to what we have done before, but it's also very different. Like, how would we approach this problem if we don't even have the original representation of the data? Okay, so there are a variety of ways to try and solve this problem, and they have different sort of objective functions. And if you actually write down the objective function and solve it, you get a different solution, the sum of squared distances, then you get a different solution than what I'm going to describe. I'm going to describe something called classical MDS, which is basically built on top of things like centering and PCA, but does not exactly correspond to the sum of the squared errors. It corresponds with some other formulation I'm not going to bother to try and write down. But this is what most people use. So this is the most basic solution of this problem. Okay, and so the kind of so I'm going to write down I'm going to write down the algorithm, and then we'll see it in action, and then I'll try and explain it. It's a little unintuitive because I'm getting these distances instead of the actual locations. Okay, but it's going to use a lot of the tools we've seen so far. So I'm going to start with I'll take as input D, this distance matrix in R n cross n, and some parameter k. Okay, so the first thing I'm going to do is I'm going to get step one. I'm going to square D. So I'm going to call this D2. Okay, and so this is going to be defined. It's not the square of it, but I'm going to square all of the elements. So it turns out it's easier to work with the squared distances. So I want D2ij to be defined as Dij squared. Okay, so I'm squaring each individual element of the matrix. So now I'm an n by n matrix with the squared distances inside of it. Okay, 2, I'm going to create a matrix M, which is a little unintuitive why we do this. That's going to be -1/2 times the centering matrix, the n by n centering matrix, times D2 times the centering matrix again. This is a step called double centering. Okay, and this is kind of going to be the equivalent of what we did with PCA, where we did centering. And why is there a -1/2 in front and all this stuff? I'll try and give some intuition of why that is the case afterwards. But we're going to think of this, the distance matrix is going to kind of act like, the insight here is D2 is going to kind of look like A transpose, the negative of A transpose. It's going to kind of look like that, where A is some high dimensional, where A is in n times, I'll call this P, some very high dimensional space, for instance. Okay, where if I did actually have a data set A, then D2 is going to kind of look like the negative of that, A transpose. Okay, I'll try and give some intuition on that in a bit. Okay, okay, step 3. Okay, now that I've done this centering, I'm going to construct the eigen decomposition. So I'm going to get the eigenvalues and the eigenvector by doing the eigen decomposition of M. So this is basically, remember this, the eigen decomposition and captures the principal components. So this is this singular vectors and singular values. So this is basically like the SVD step, but because it's a square matrix, we're using the eigen decomposition instead. Okay, and then 4, I'm going to return this set Q, which is going to be VK, which is effectively the top K eigenvectors, right? Which are the right singular vectors times LK to the power 1/2. These were the eigenvalues. Remember, these are the eigen. So these were the eigen, or the top K eigen vectors. Okay, and these are the square root of the eigen values. So these are basically the singular values, right? Because the eigen values are the singular values squared, right? So I'm multiplying by the singular values. That tells me how much to stretch it out. Okay, so this is the algorithm. So this is the classical MDS algorithm. So it should look a lot of familiar parts to us, but why it works might be a little bit kind of unintuitive here. Okay, so I think what I'm going to do is that I'm going to show you some stuff in Python, and then with some time we have left, I'll give you some intuition on why this is the right algorithm. Okay, there's a full couple page explanation in the book, and I'll probably give you the first half a page of that, which will give you a lot of the intuition of what's going on without getting into all of the technical details. Okay, so let's let me switch over to my Python window here. Okay. Okay, so, and these are now linked off of here. I'm going to first show you, we skipped over just centering. Let me just show you a demo of centering first. I'm loading in a 3x2 matrix here, right? 1x5, 2x3, and 3x10. And so I can compute the mean of the X value. The mean is 2, 1, 2, and 3. The mean is 2, and the y value 5, 3, and 10, the mean is 6, right? And then I can do this A minus the outer combination of ones. This kind of subtracts them off element-wise, and this is the centered matrix. If I look at every column here, the mean should be 0, right? If I add all these columns up, the mean is going to be 0. I can also do it through the centering matrix. I take the identity matrix and I subtract off this ones matrix here divided by 3 in this case. Okay, and this will give me this centering matrix. And you can see that this is the centering matrix, the identity minus 1/3 everywhere. Okay, and it's got some, yeah, it's going to give basically the same answer, except this one, you know, this is supposed to be 0. There's some rounding error. So it didn't quite give me 0 here because of 1/3 doesn't quite get represented correctly. But, oh, can you maximize the font size? Yeah. See if, hopefully that's better. Great. Okay. So this is basically 0 here. And then, okay, and then let's plot these. So I'm just going to plot them before. This is in red. I'm applying them beforehand in red, and I see, look, this is 1, 5, right? And 2, 3, and 3, 10. But then I centered them, and now the origin is right in the middle in the blue dots, right? That's here. Okay, so that's centering. I get the same answer both ways up to rounding errors. Okay, so pretty simple. Let's do MDS. For MDS, we're going to use a little bit bigger example here, where I'm given this distance matrix, and I've designed it so the distance is going to be symmetric. But in this case, it's not going to be a positive definite sort of matrix here, which we'll see is going to cause some weird issues later on, but we can still run this on this problem. So this is not going to actually be a metric. I think there's some triangle inequality violated someplace. Okay, and then I've squared every individual element. So between elements 1 and 2, or 0 and 1, depending on your index, these are both the same. And then I square them, and 4 becomes 16, right? 3 becomes 9, 7 becomes 49, and so forth, right? So that's what this D2 matrix is. Okay, and then I'm doing this, create this centering matrix. Okay, and here, create my centering matrix, C. And I'm going to apply this double centering operation here. Create this matrix M, minus 1/2 C times D2 times C again. Okay, centering on both sides. Okay, and now I think it's such that every row and every column is going to have a 0, is going to have an entry of 0. And we'll derive where the minus 1/2 comes from in a bit. But that's what the double centering is giving you. Now we can run the eigen decomposition. Okay, and these are going to be my eigen values, right? And I'm going to get some imaginary components here, which is kind of a pain. It only happens at the end, right? This is the first one, 5.2 with basically no imaginary part, 8.1 with no imaginary part, minus 3.5 no imaginary. So the first ones don't have any imaginary parts, but towards the end it does. It's going to have some. Oh no, it doesn't here. They're all just rounding errors. Okay, but then I printed. Yeah, so this is the first element of V. Let me. Okay, yeah. So this is, then these are the singular values, are these columns here. So a singular vector. The eigenvectors are the columns of this matrix V I printed out second here. Okay, but we're going to want to use these, and we don't want imaginary numbers lying around. So I'm going to take the real part here. Okay, and to take this matrix s, remember I want to take it to the power 1/2. So I want to take the real part. So I'll take the power to the 1/2 first in case I get more imaginary numbers. Oh yeah, because I have a negative here. So this negative is, I can't take a square root, or I can, but it's going to be imaginary. But then I'm going to take the real part here. So that I'll just take the real values. There could be some weird stuff that happens if I have all imaginary things here, but this is typically ignored. If the original data can be embedded in some high dimensional Euclidean space, everything will be real. But if not, you might get some imaginary weirdness going on. But this is still what everyone uses. Usually it's not a problem. Okay, and then I'm going to recover it by taking the first 2 dimensions. I'm going to get it down to 2 dimensions. Remember, this was 5 by 5, so I have 5 data points. I'm going to get down to 2-dimensional space, and then I'm going to get my diagonal matrix S, and this was after I took it to the 1/2 already up above here. Okay, so I'm going to get S2 is now, these are basically the principal values, or the singular values, which is square root of the eigenvalues. Okay, and right, and then I multiply these together, and I'm going to get Q, and these are my data points, and I can plot them. Okay, and here are this representation of my data points. Okay, so let's go and look at, yeah, so the first one is -3, -2. So this is the first data point. The second one is -2, 1.6. So that's going to be the second one. This distance looks to be about 4 apart, right? This distance was about 4. Let's go and check what the original distance was. The original distance between them was 4. So it did a pretty good job. Let's look at a different one. This one was supposed to be 8. This was data point 1, the first data point and the last data point. That distance was supposed to be 8. Let's see, the last data point is 4 minus 4. So that one is, the x value is 4, and the y value is about -4. And so this distance was supposed to be 8. It looks like, yeah, from about -3.5 to about 4.5 and a little, yeah, so it's pretty close to 8. So we did pretty good about preserving that distance. Okay, so this seemed to actually preserve these distances that we originally were trying to get here. Okay, any questions about the code? It's up online. You can play with it a little bit. But let me try and give you a sense of why this is working for the last 5 or 6 minutes. Okay. Where is that screen? All right. Okay, great. This is back. And okay. Okay, so why does multidimensional scaling work? Or why does classical MDS work? Okay, so, okay, the key insight here is going to be looking at, is we're going to assume there exists some A1 through AN, so D of AI, AJ equals DIJ. Right, so we're going to assume that there's actually some data points that are in Euclidean space. Okay, and in fact, that this is AI minus AJ. So we're going to assume that there is some data points with the right Euclidean distance here. And we're going to use this expansion. So if I look at these data points and I look at the squared distance, which I have if I get my D2 matrix, okay, and I can write this as AI squared, the norm of AI, plus the norm of AJ squared, minus 2AI inner product of 2AI AJ, right? This is just this typical, I'm just expanding this so quadratic form of the norm, and you can show that you can rewrite Euclidean distance into this way. The norms of AI and norms of AJ minus 2 times the inner product. If you did, if you aren't sure about that, if you remember that this is equal to A squared plus B squared minus 2AB, right? So you've probably seen this before from algebra or something, and the same thing is going on here. So if you believe me that you can do this expansion. And so then we're going to do a little bit of algebra. Okay, so then I want to solve for this inner product. Okay, and this is equal to 1/2 times, and this is where that 1/2 is going to come from in the double centering step. AI squared, AJ squared, minus AI minus AJ. Okay, and so this inner product is useful because if I write down A transpose, right? So let's say that A equals A1, A2 up to AN, right? This is a matrix in NP, right? There exists some high dimensional matrix. I don't care what the dimension P is, but it's something big. Okay, if I look at this guy, the ith J coordinate is exactly this inner product. That's what multiplying those two matrices together is doing. The ith J element of this n by n matrix is going to be AI dot AJ. That's what this matrix multiplication is doing, which means that this is equal to 1/2 DI1. So this is, yeah, so this is equal to 1/2 AI squared minus AJ squared plus, should be a plus there, minus DIJ squared, right? And this is a quantity that we have. This quantity is given to us, and if we have this quantity here, or if we have kind of this quantity A transpose, we can do the eigendecomposition and do get a projection into a low dimensional space, right? So if we have A transpose, we know how to use the eigendecomposition, and we have this blue part, we have this squared distance, okay? But we have these other terms here. So we want to get something like A transpose, but we have these other terms, but there's 1 degree of freedom. So the trick is assume that A1 is equal to 0. If I assume is, in fact, the origin, so 0, 0, 0. So it's the all zeros vector. Then I know the distance to that one is 0, and I can say the distance to everything else is then this is equal to 1/2 DI1 squared plus DJ1 squared minus DIJ squared. Okay, so these guys I now get because the norm, for instance, if I look at this one, that's the norm, that's the length of the AJ vector from the origin. but the origin was where the first data point was. So I have the squared distance of the first data point. I can assume that it's the origin, and then I can substitute that in, and so then I can recover this A transpose kind of matrix, right? So I have all of these terms here. Now I've got this term from input, and I also have these terms if I assume that the point A1 is going to be at the origin. Okay, and this allows me to reconstruct A transpose, element-wise, and then I can do the eigendecomposition and project, and that's what the rest of the algorithm is doing. Okay, so this is almost there. I've got, and if you look at these elements here, I've got this 1/2, I've got this minus sign, I've got the D2. These were all common things we had. But then I have these other terms here, right? I've got these other terms that have to do by assuming D1, or the first data point, was at the origin. And basically, I want to average over all these. If I average, on average, every point is at the origin, that's what the double centering is doing. And I'm centering on both sides because I have A transpose. So I need to center both A and the A transpose. And so I put the centering matrix on both sides. And effectively, that averages it's out. To see that why that's the case requires a bit more algebra to go through, which I'm not going to go through. But this is kind of essentially why this classical MDS works. Great. So we're out of time. I'm going to stop here, and I'm around for office hours. Don't wait to get started on the next homework. There is a component that's going to take a little bit of time again. Hopefully the demo video gets you over any humps you had from last time, if you haven't already figured that out. Okay, great.